Thanks, Marietta. Well, as Marietta has said, this webinar is about how accurate are domestic water meters in the real world, and it's an EMPIR-funded project called MetroWaMet. About me, I've been involved in this project since I started at NEL just over a year now. I have been working with the water industry both in the UK and overseas for most of my career. I'm also involved with the standard committees ISO TC30 SC7, responsible for ISO 4064, and OIML TC8 SC5, responsible for R49. And my screen is not responding. Aha, here we go. Right, so I'll start off with an introductory background to the project. Then I'll go through the work packages involved in the project, which are the effect of unsteady flows on meter recording, the effect of water quality on meter life, the measuring the ability of meters to detect leaks, and the development of a virtual flow meter. So, domestic water meters are tested to ensure that they conform to prescribed levels of accuracy. And these are enshrined in international standards and regulations with the test procedures in OIML R49. And these test procedures are carried out over the meter's flow range under constant flow rates in ideal conditions. But in the real world, flow rates are not constant. Anyone who has listened to their washing machine or dishwasher knows that the water is allowed in short bursts, and then a wait, and then another short burst. Showers are, of course, a much longer, more constant flow, but other domestic activities like hand washing or filling kettles are again much shorter. Does this pattern of usage affect the meter accuracy? Also, the test procedures are usually carried out with water from the local public potable water supply, but there are variations around Europe, and how much will that affect the meter performance? Smart meters are also becoming more common in water networks. And how well can they detect leakage, and what criteria should they meet to be able to detect leakage? Can we estimate in advance how a meter will behave under different conditions? To answer these questions, this project was set up. MetroWaMet, short for Metrology for Real-World Domestic Water Metering, funded through EMPIR. And the project aim is to establish a metrological infrastructure which will enable an integral characterization of domestic water meter performance close to real-world conditions and not at laboratory conditions as presently done. The project started 2 years ago now, in June 2018, and is due to finish in May 2021. If you want to find out more about Euromet, EMPIR, or MetroWaMet, the websites are listed there, but actually it's quicker just to do an internet search for the keyword. As well as the partners in the project, we also have an advisory board with representatives from stakeholders such as meter manufacturers and water companies. And these are the participants in the project. We have RISE in Sweden, VTT from Finland, DCI and FORCE from Denmark, CMI from the Czech Republic, TÜVSÜD from Turkey, UNISA, the University of Salerno from Italy, BEV PTP from Austria, CETIAT from France, PTB and DVGW from Germany, and us from NEL, the National Engineering Laboratory from the UK. So on to the first work package, measuring the effect of unsteady flows on meter recording. The organisations involved in this work package are the majority of the participants. As you can see, all those their logos there. And as mentioned before, this work package measures the effect of unsteady flows on meter recording. The domestic water meters have to comply with OIML R49, which sets out the requirements for testing and type approval of domestic water meters. And these tests are limited and they're carried out under steady state conditions, whereas the actual usage is less predictable and dynamic. So the purpose of this work package was to create test rigs that can dynamically test water meters to determine whether a more rigorous test regime of these meters is justified. So the first thing to do is to establish a reference load profile. And this would establish design requirements for the various test rigs. And this would be based on prior research and also consumption measurements undertaken during the project. The first thing to do for the sampling for consumption measurements was to undertake a site identification scheme. So it was important to create a common set of guidelines for selecting the various sites. Across Europe, there is variation of usage, the measurement technology, the household makeup. So a statistical approach was used for site selection. And the site identification scheme suggests how the sites should be identified by looking into various socioeconomic factors, average household sizes, average income in the area, the types of households, and the industry in the area. And from this, making a representative selection of sites, but also random. The type of industry is quite important because the consumption patterns vary if all the people within the area are working 9 to 5, or if it's a heavily industrial area where people are on shift work. And here is an example slide from some measurements undertaken by CMI in the Czech Republic of 2 flats. And this just plots the daily consumption over a period of 15 days. And as you can see, the daily consumption varies quite widely. Clearly, there were days when the people were not at home. And the consumption typically, well, the average consumption is really quite low, but these are flats and probably with a single occupancy. And this is the data plotted out with flow and pressure against time. And as you can see, there's a considerable variation of consumption in the period under review and the consumption against time. The consumption is very peaky, so there's periods with almost no flow and then sudden peaks as people use water-consuming equipment. The consumption measurements are then converted into histograms where the frequency or the time spent at each flow rate is plotted. And as you can see from these graphs for the 2 flats, most of the flow happens at very low flow rates, below 0.1 litres a second, and much less of it is at the higher flow rates. They also did measurements of hot water consumption, and the histograms were similar. It was rare that flow rates were higher than 0.3 litres a second, and the absolute maximum for both flats in both measurement periods was 0.72 litres a second for cold water and 0.5 litres a second for hot water. Consumption measurements were also undertaken in Turkey, where a commercially available volumetric meter was modified to give 60 pulses per litre, and 3,200 flow events from 4 sets of measurements were analysed. The flows were grouped as single amplitude and multiple amplitude, where single amplitude is one appliance in use only at a time, and multiple amplitude where, say, somebody's having a shower and the washing machine turns on. And around 15% of the events are multiple amplitude, so the obvious corollary to that is that 85% of the events are single amplitude. This is the data from TÜV. On the left, you can see that the consumption was the volume passed against time, and consumption varies in a non-linear manner with time. The center graph shows the peakiness of the consumption, and on the right there's an expanded graph to show a little more detail. The findings were that 60% of the events were shorter than 10 seconds. The maximum amplitude and flow rate is below 40 litres a minute, that's 0.67 litres a second, which ties in well with the Czech Republic results. And for most of the events, the rise time from 0 to full flow is very short, within 0.2 to 0.4 seconds, as is the fall time as the water is switched off. So to create the dynamic load profiles, there was an algorithm set up to generate the test profiles to be used in the tests. And this is based on the empirical data from the Turkey, the Czech Republic, Denmark, and Germany. And this was valid for meters with a Q3 of 2.5 meters cubed per hour between R40 and R800. I'm sure that virtually everyone on the call is familiar with the way domestic water meters are specified, but for those who aren't, just a quick recap. Domestic water meters are defined by 4 flow rates, which unsurprisingly are called Q1, Q2, Q3, and Q4. Q1 is, to quote R49, the lowest flow rate at which the meter is required to operate in a satisfactory manner within the maximum permissible error. Q2 is 1.6 times Q1. Q3, again to quote OIML R49, is the highest flow rate within the rated operating conditions at which the meter is required to operate in a satisfactory manner within the maximum permissible error. Q4 is 1.25 times Q3, and the R number is the ratio between Q3 and Q1. And the required accuracy of the meter is plus or minus 5% for flows below Q2 and plus or minus 2% for flows above Q2. So the algorithm that was set up generated a test profile similar to the one on the bottom left-hand corner there, and then which extracted flow points and combined them with their mean duration. And to check that this was representative, the flow was integrated over time to give a cumulative distribution function, which was compared with the original data. There were dynamic test facilities were built at 7 laboratories, as shown here. Following the building of the test facility, there was going to be an intercomparison sequence where a reference flow meter is passed between all the different labs before the full test program starts to ensure that all the labs' test facilities are giving comparable results. Though labs use various means to control and measure the flow, at PTB they have a cavitation nozzle apparatus which has 6 different sized nozzles, and pressure downstream is vapor pressure. So each of these nozzles can be switched on very quickly, on and off very quickly, and the flow rate is fixed by the upstream pressure. And the different flow rates can be achieved by different combinations of the nozzles. If you look at the graph at the bottom and the item number 4, you'll see that as the different flows are generated, the different nozzles switch in and out. And this gives repeatable and reproducible dynamic flow profiles. At Setiat, they have a dynamic gravimetric test rig where the water is passed into a weigh tank, and the weight of the tank is recorded against time. And from the weight, you can obviously, through the liquid density, get back to the volume against time and the flow rate against time. The test rig can vary flows between 1.3 milliliters per second to 4.2 liters per second. So that's 5 to 15,000 liters per hour with an uncertainty of 0.1%. They can work with upstream pressures up to 6 bar and water temperatures between 10 and 90 degrees Celsius. And for the various valve arrangements, they can generate dynamic flow changes of different types, steps, oscillations, ramps. And they can perform static and dynamic calibrations of any water or flow meter. You can see the weigh tank at the bottom of the screen, second photograph to the left, and the dynamic flow generator to the far left. At DTI in Denmark, they also have a gravimetric test rig, and here you can see a photograph of their weigh tank and of the control valves. The rig is software controlled to control the duration of any flow and the magnitude by using the various valve positions as well as pump speed. And they can achieve flow rates up to 15,000 liters an hour, which is 4.2 liters per second, at water temperatures between 5 and 85 degrees Celsius. And they have software for automatic dynamic flow calibration and continuous fast sampling of the gravimetric measurements rather. There's another photograph of the valve set up for the dynamic flow tests and a graph of the gravimetric-based dynamic flow records. And obviously the data is sampled and stored for later processing. At VTT in Finland, they've also got a test rig for dynamic flow measurements, and they're using water from the local water supply network with a pressure of around 7 bar G and a water temperature of around 5 degrees Celsius. And they control the flow using gate valves, often starting from 0 to imitate the household system. They too use a weigh tank, which can hold up to 800 kilograms of liquid, and which outputs data in the current step value of 10 grams, i.e. 10 milliliters of water, and they're working on improving it to 1 gram steps, and also getting the output with exact time steps. They also have fast pressure and temperature sensors. The flow is controlled by 4 different valves. They've got 3 fast on-off valves, which open and close in less than 30 milliseconds, and they've got 1 control valve for ramping. At Rise's dynamic test rig in Sweden, they've got flow rates controlled by digital valves with near perfect linearity, and they're pneumatically controlled. And this test rig, instead of a weigh tank, so it's not a gravimetric system, they use a piston prover, which is a cylinder which is constructed to very close tolerances with a piston that moves within the cylinder, and the location of the piston within the cylinder is recorded against time, and obviously if you multiply the position times the area, you'll get the volume. At CMI in the Czech Republic, they have got a dynamic test rig with both a piston prover and a weigh tank. They can test water between 10 and 90 degrees Celsius and operate between 0.3 and 6 bar for these tests, and the rig can withstand a maximum of 16 bar. The volume of their piston prover is 30 litres for one test sequence, with a minimum flow of 0.6 millilitres per second and a maximum flow of 1.9 litres per second. That's for the dynamic measurements, and for steady state flows, they can use either the piston or the weigh tank. The weigh tank has a volume of 550 litres. The minimum flow is determined by the piston prover at 0.6 millilitres per second, and they can accommodate a maximum flow of 17 litres per second. And for sort of ambient temperature measurements, piston prover has an uncertainty of 0.06% and the weigh tank 0.1%. At Force in Denmark, they've got what they describe as a semi-dynamic test rig. Again, it's a gravimetric test rig with a weigh tank, as you can see in the left-hand photograph. And on the right-hand side, you can see the valves, the control valves. The weigh tank can contain up to 200 litres of water. The rig can work with temperatures between 5 and 90 degrees Celsius, with flow rates between 0.3 millilitres per second to up to 1.7 litres a second, with a target uncertainty of 0.1%. And like one of the previous test rigs, the flow profile is generated by a combination of valve position and pump speed regulation. CETIAT is providing the validation module, the transfer standard, which is an Emerson micromotion Coriolis mass flow meter, which can read up to 1.1 litres per second, 4,000 litres per hour full scale. And it has a variety of outputs. It has a digital output with dedicated software and pressure and temperature sensors, with a 20 Hertz sampling interval for sampling rate for flow, pressure and temperature. And it's all been neatly put into this shipping friendly package to be moved between laboratories so that they can use the same reference meter to test all the different test rigs. The planned timeline for this work was for the spring to early summer, was the individual labs creating their test rigs and validating they could perform to required specifications using the CETIAT's validation module. The early summer 2020 was to adjust and correct any deviations from the specifications. Between summer and autumn this year, the intercomparison of all test rigs, and autumn to winter tests on commercially available water meters. Unfortunately, the coronavirus has rather hit these, with the laboratories being closed, and so the progress of this has been delayed. The extent of the delay is currently under discussion, but we're hoping that it's only going to be about 3 months. The planned outputs for this work package are some recommendations as to how to acquire consumption profiles. And these will include guidelines to select equipment, timescales, and sampling rates. There'll be a technical guide for the assessment of the performance of domestic water meters under dynamic load changes beyond the current method specified in OIML R49, and contributions to or influence on the international guides and standards, particularly ISO 4064 and OIML R49. The next work package is looking at the effect of water quality on meter life. And again, most of the participants are involved in this work package. The work package undertakes the following steps. Firstly, a representative selection of domestic water meters, representative for the European market, that is. And a determination of which metrological parameters to use. Also to determine which parameters of water quality to be used in the experiments based on a survey. And then to decide on the distribution of the different water meters, the different tests and methods between the various partner laboratories. And to come up with a so-called cooking recipe for the quality of the waters to be tested. So there's going to be two sorts of tests: static tests under the conventional continuous test regime and under dynamic load changes. Looking at the measurements on the water meters on the various water qualities, and to evaluate the results as to the sensitivity of the various water meters to water quality, looking at hardness, pH, and suspended particles. So the meter types have been selected based on a survey of the domestic water meters currently in use in the various countries in Europe. And the ones were chosen were single jet, multi-jet, piston, electromagnetic, and ultrasonic. The types of meters selected was further refined, or technical meter parameters. So the nominal flow rate Q3 of 2.5 meters cubed per hour, the diameter, the nominal diameter of 15 and 20 millimeters, and the ratio of Q3 to Q1 from R80 to R400. The other aspect of meter installation that's being looked at was whether being installed horizontally or vertically made a difference. So they're looking at horizontal installation with the dial facing up and vertical mounting positions. So the water quality survey was based on a survey of typical operating conditions in water quality around Europe. So it included the results of a Europe-wide survey of inorganic chemical composition of tap water quality, and age and wear effects were also targeted. And the graph on the right, which I realize you won't be able to read, shows the proportion of the European countries exceeding the threshold requirements. So there are some aspects that are barely exceeded, and there are some that are exceeded by quite a few countries. And these, of course, were the ones that were targeted. The conclusion that was come to is that high quality drinking water is used across the EU, fulfilling the Council directive. Some parameters either exceeded the limits or were highly placed, and these were taken into consideration when selecting water parameters to model. I mean, in particular, there was iron and there's a colony count at 22 degrees Celsius, coliform bacteria, manganese and chloride, and a lot of those were due to possible corrosion processes. There are a number of microbiological parameters, coliform bacteria concentration and colony counts, that are due to biofilms, which has a potential influence on the functionality of a water meter, but was not something that could really be tested in this project. And conductivity and hydrogen ion concentration have also been partly exceeded in some member states and have been reported as potential influence factors on water meter functionality. So the types of water meter, the ranges, and the installation positions were varied across the various laboratories. These are all the test laboratories, and these are the meters being tested, the position at the test rig, so horizontal dial up, vertical, the range, and the type of meter. and it was ensured that each meter type and installation was tested at least 2 laboratories. There was also a variation in the water parameters being tested at each laboratory, and again at least 2 will be tested at each laboratory. There was particle concentration, everyone was testing hardness, most were testing pH, and some of the tests were carried out at will be carried out at constant flow and some under dynamic flow. And the specification of these various aspects are in the so-called cooking recipe that's been developed. So the cooking recipes contain different concentrations of the parameters, low, medium and high. So total hardness, pH and particles, which are iron and quartz sand. And there's already been an exercise for calculating the concentrations and selection of necessary chemicals and define a base model water. And then starting from the base model, the chemical parameters are adjusted for each experiment, which gives you the model waters. And there have also been tests to check that the model water remains stable with time. The performance tests will either be conducted in model networks or test rigs, looking at 11 days for each performance test and the throughput for each test of about 200 meters cubed. And as mentioned before, either at constant or dynamic flow profile. And the chemical parameters are frequently monitored during the test to ensure stability. And then before and after each performance test, the determination of the meter accuracy at the 6 nominal flow rates specified in OIML R49.1. So the results of the performance test will increase the knowledge of the influence of specific water quality parameters on the measuring accuracy of the various meter types. The planned outputs from this work package are a report on the performance of the domestic water meters varying with water quality, i.e. hardness, pH and particles, and a good practice guide for the testing of domestic water meters with different water qualities as investigated in this work package. And on to work package 3, which was measuring the ability of meters to detect leaks. And these are the organisations involved in this work package. So this is to do with leak detection and low flow, and it's well known that different types of water meters perform differently at low flow depending on their measuring principle, which affects the starting flow, i.e. the flow at which they start to register consumption, and their dynamic performance. And all meter types have different cutoff values at low flow. If you have a mechanical flow meter with a rotating wheel, it needs some flow to overcome friction before the wheel begins to turn, whereas an ultrasonic meter has no mechanical parts or force to overcome before measurement can start. So the purpose of this project was to look at the performance of different types of flow meters at low flow and also for different dynamic flow profiles, and investigate flow patterns together with imposed leakages. Also to develop algorithms to detect leaks and an electronic solution for leak detection. And 3 different dynamic profiles for low flow, defined as under 30 litres an hour, have been developed in the project for comparison of meter performance. The standard dynamic profiles will be used across the various laboratories to allow methods for calibration for low flow with known uncertainties. And there's an example graph on the right showing the comparison between a high precision flow meter and the dynamic flow using gravimetric, i.e. weigh tank method. An online survey was carried out to look at smart metering and leakage detection across utilities in the EU. Approximately 30 water utilities participated. Most of the utilities were Danish, but there were also German, Turkish and Italian utilities. There was only one utility who said they performed no leakage detection at all. Other utilities either performed leakage detection inside the dwelling, downstream of the meter, or distribution network leakage detection. 40% explicitly stated they carry out post-meter leakage detection. And the most frequently applied method for leakage detection is the minimum night flow, followed by 68% of the utilities, followed by flow pattern methods, 32% of utilities. So what is leakage? It's an unwanted deviation from the normal state. So they're looking for, so any algorithms developed should be able to identify normal patterns without leakage and abnormal patterns with leakage. And then the deviation will then be identified as leakage. So the plan is to look at cluster analysis to determine normal and abnormal patterns. They also have an image-based add-on module for detecting slow rotation of digits on a household flow meter by taking images of the digits and comparing images to the previous one and correlating how much the images are alike. It can be estimated how much the digits have moved. So in the top graph, the sort of T0 and T1 images show almost perfect correlation. So the digits haven't moved, whereas down below, you can see that the digits have moved from 1 to almost 2, so the correlation is much lower. The planned outputs for this work package are a technical report describing algorithms for the detection and evaluation of leakage, and a report and recommendations for leakage detection using smart meters in households, and recommendations for the data infrastructure for leak detection and quality assessment. And onto the last work package, the development of a virtual flow meter. There are fewer organisations involved in this work package, so PTB, DVGW, VTT and TÜV. So what is a virtual flow meter? It's a computer simulation to simulate the effects of operating conditions on the performance of the water meter, to estimate the deviation, uncertainty and predict effects due to aging and wear. And the input parameters have been identified in work package 2, and the experimental results of the effects of the parameters are again from the model networks of work package 2. And the output is designed to be an openly accessible web application with no barriers, with user-defined input based on a database that's both modular and expandable. Water suppliers and manufacturers would then be able to predict the measurement deviation of the meter after various periods of time based on the parameters in their network. So the input is the results from work package 2, which then goes through the process and gives an output. And here is an example. So, for example, a meter type A from a typical household metering technology would, when new, give the result at T0, the black line here, which fits within these maximum permissible errors of 5% and 2%. You then apply parameter 1, e.g. particles or hardness or pH, and then you look at the effect over time. And after a certain time at T1, you can see that the calibration might have drifted a bit. At T2, it's drifted further. At T3, and drifted even further. And then how this is used for, here you've got the measurement deviation against operating time, and here are the measured deviations from T0, T1, T2 and T3, and then beyond T3 these measurements are extrapolated with increasing degrees of uncertainty. And then for a different parameter, parameter 2, and these are the measured deviations, and this is how the deviation is predicted to continue against time. So the virtual flow meter is designed, as I said before, to be modular and expandable, so that it can include further measurement results, either from additional types of meters or additional quality parameters after the end of the project, and then a Europe-wide harmonized and accessible web application will be available for use by anyone who wishes. The planned outputs from this work package are the report on a database to estimate the performance of the water meters, depending on the various parameters related to water quality. Also a paper on the virtual flow meter and its capabilities, and how it can be used to assess the metering quality of domestic water meters for typical European operation conditions based on a given set of input parameters, i.e. meter type, water quality and time span. And that's all I really have to say, other than to again acknowledge the funding provided by EuroMet through EMPIR to support this project. If you'd like further details on the project, please visit the MetroWaMet website. The URL is there, but it's probably easier just to search for MetroWaMet.